Let's continue what we did. Okay, there is one more thing we did last week. There's one more thing we did last week. We applied the divergence theory. We apply this theory. Okay, we don't need to remember this. You can find this theory from your appendix. Okay, from your appendix. Use the divergence theory, apply your divergence theory to your Maxwell equation. This Maxwell's equations. Okay? Use this one, apply to this equation. Try to explain this is Gauss's law. Okay, this is our goal. To explain this is true. Okay. So first of all, we have the Maxwell equations. I don't know how many of you still remember this stuff. The first step is we try to take a volume integral to both of left and the right hand side of these equations. Okay, we take the volume integration dv equals to rho dv. Right? There's nothing special, right? You check the volume integral to left side and the right side, both of them. You know, if you take, this is a density, current, the charge density, volume charge density. So if you take a volume integration to your charge density, this part equals to Q, means how many charge you have for this volume, right? One problem. But for your left part, you can use this divergence theory to change. If this is A, your vector D is vector A, you can change this form to a closed surface integration to, okay, now this will become dx. Okay. You find a connection between Q and your closed integration, surface integration of your D. Okay, electric charge flux density. You take an integration. You can also change your D to epsilon E, right? You know your D equals to epsilon E. You can also write down like, okay, this is epsilon E. Try to organize it. Because if this is for this surface, inside this surface, if your material is uniform, your epsilon is all the same inside your material, you can take your epsilon outside your integration, right? Therefore, you obtain your surface integration of E for a closed loop of the surface, closed loop integration, surface integration equals to Q divided by epsilon. This is epsilon, this is E, okay? They are different, right? Epsilon and E there. Looks similar, but they are different, totally different things. And actually, this is Gauss's law. If you take an integration for a surface, the closed surface, area of a closed surface, you know how much charges, how many charges are there inside your material. Okay? Gauss's law. Alright? How about this one? This is another Gauss's law, right? You know the Gauss's law for a magnetic field. If you change your D to B, your dou to 0, you change this one, D to B, dou to 0. Let's do that. D become B, dou become 0, and this one is B, and for this part you have nothing because you don't have the magnetic charge, you have only electric charge. And for this one, B equals to mu multiplied by H. So you finally got 0. You can take a B or you take a H. You got the same result, right? Either you multiply mu or not, because for the right hand side is 0. Okay? You guys follow? Okay, let's see the slide. We spent so many times for these 4 Maxwell equations. I think maybe many of you should remember it. It's not very hard to remember. You take a curl to E, you take a curl to H. You take a divergence to D, it's very E and become D, right? And you take a divergence to B, comparing to H, right? And equals to, for this part, you need to take the partial differential to time, minus and minus m. This is hard to remember, I know, at the beginning. But for the second part will be easy. Second part is a positive. You also take a partial differential to time plus J. J is related to current. I, it is the current density. If you take your current, if this is the unit current for 2D space, you will have a current density. We can see what is J. See? It's ampere divided by m squared. It's like how many how many current, how many amp you have, divided by the area. So J is average. You think like a density of current, okay? So for this part, this is the electric flux density, electric current density, okay? You can think like, okay, E, H, H, E, okay? And then this is E, E, H, H. Think like this way to remember that. You take a curl E, curl H, you get a divergence D, divergence H. Try to remember it. After you see that again, and again, and you understand. So this is a differential form of time-varying Maxwell equations. This is what I'm asking for. Okay, what you write down there. And this is a relationship for a free space. Then when you apply divergence theory, you can transfer your differential form to integration form, okay? And see what is the result for both of them. Is why this is the integration, right? This is the integration. See, you take an integral, closed surface integral equals something. This is the integral, right? Equals something. Okay. So this is Gauss's law. I copied this page from Wiki. You can Google your Wikipedia for Gauss's law. You can see this equation. Did you see that this equation is totally the same as what we write? We just write out here. Okay? This is Gauss's law. And the scientists measure the result. This law came from your experience. Okay, you don't think about it. You can use the Maxwell equation to obtain the same law from the experience and also the quantity. There is another very similar. You also apply your Stokes theory to first and the second equations. You will obtain similar thing, very similar thing. Okay, but of course it's a little bit different. Maybe you can try by yourself because very similar, but it's more difficult because you have two terms for the right side, right? That's okay. It's okay. You take this is also this is a surface integration, but it is not a closed surface. It's only one surface. It will equals to if you take a surface integration of the area, the result will become some closed integration of the line integral. Okay? For this part, this is for one surface, only one surface. It's not the closed surface. It's just only a piece of surface. And the result will become a closed line integral, the red one. Okay. So apply this to first and the second. You obtain these two equations. For lane, what are they? For the first one, you can see. For this one, it is a current. As I say, this is a current density, right? So you take an integral for a surface, you obtain your total current. your current. So the first one, it will become Faraday's law. Faraday's law means if you change your magnetic field, you will induce the current. If you ever do the experiment for this one, you change your magnetic field. You change that, you have a EMF. This is induced electric field. Okay. If you change your magnetic field divided by time, your magnetic field is changing according to time, and you will obtain this result. Okay, and also I think people are more familiar with Ampere's law. For the second Maxwell equations, you apply the Stokes theory, you will obtain this equation. Okay. Then this is Ampere's law. If you take an integral of your magnetic flux density, you will obtain something related to the current. Okay? If you have a current goes through a core line, then you will have a magnetic field around it. Okay? So those four equations, the first equation is Faraday's law, second one is Ampere's law, and the third one and the fourth one is Gauss's law. These are the integral form of time-varying Maxwell equations. Okay? Those are from the experience. Okay? You can observe from your experience. Are you okay? Okay. Those are very famous laws, right? So I think maybe you can Google it from somewhere. Okay. One more thing. Can we simplify this equation? Can we simplify the equation? Because the equation, as I say, is too hard, right? Too hard. You have a component you have variables come from x, y, z, and t, right? Do you have some rules happen again, and again? Then finally, I don't need to deal with. I can take it sometimes out. Okay, take some part of it out. Yes, we do. Because for these microwaves, they will repeat the result according what? Time. Right? You are changing according to time. They will repeat again and again and again with time. Remember when we took a class that semester, remember we used something cosine omega t, right? Remember, right? Or you say this is cosine omega t is theta. Do you remember this one? You repeat the time again and again. So you already know what happened for the time, for this part. You don't need to do that every time, right? Okay. So what we can do to simplify this equation? Okay. We call that we change our cosine to phasor form. Can any of you still remember what is the phasor form? One more. Okay. Next question. Who is next? 正能方体 I ask you ready? I ask you no. 那件事 I ask you already. No, you didn't. Okay. Try to answer my question. Do you remember our last class? How did we deal with something related to time? How do we do that? Cosine, we call that cosine omega t, right? Right. And then we also call it cosine theta. Yes? Remember that? Do you have some memory about the class last semester? You do? Okay. So is there any way we try to change this one to the phasor form to make it easier to calculate? Do you remember phasor form? Do you remember that? No? Okay, let's take a break. Let me help you to review. Okay, I just repeated what I said in the end of the last class. Because your time, maybe you say cosine omega t, this part is repeating again according to the time, right? Repeating again and again. How long will it repeat again? One cycle, right? You know, in Chinese, 周期. You repeat for a cycle for your time. You repeat your cosine function again and again. You don't need to deal with this special case because this is a regular case. You don't need to make it like a function. You don't need to put it like an unknown function. You can just take it away from it. So finally we can change our result, all of them. According to this information, exponential j omega t is the only part we deal with the time. Let's make something to simplify our original differential form Maxwell equations. From the time varying to this is time harmonic. So it was time varying. We don't know how time works. Okay, how it works with time. We change that to time harmonic. You can think like your function will change according to the time, repeating with time, again, repeat. Okay. So your electric field, E, it was a function of x, y, z, and t. You try to make it easier, right? So you change that to E. Okay. Finally, we can use a common notation of the electric field to only x, y, z multiplied by exponential j omega t. Okay, understand this one? You take the time part outside, and then this one become more easy to understand. You have only variables with only x, y, z, no t. T is taking outside. Okay? Then you also have your h. Your take become h capital H, X, Y, Z, and multiply explanation J, omega T. Okay? And actually, all your vectors, those was time-varying vectors, become time harmonic. You do the similar thing to all of the vectors. Okay? Not only E and H, but also your D and B and M and J. You take apart time outside. Deal with that data. Okay, so finally, remember this word. This is the key word. Time harmonical form of the differential Maxwell equations. Time harmonic. It's not time varying. Time varying is you have the time as a component. Okay, so. One more thing. Do anyone can raise your hand to tell me how to you deal with this part? If you have something, if your B, let me just write down. B, your magnetic flux density become capital B multiply exponential J omega T. Okay? What happens if you take partial differential? If you take a partial differential to T, this one become right? So what is this one? You maintain the same thing, but you take a J omega outside, right? So you will become J omega B multiply exponential J omega T. It looks like your partial differential respect to T equals to J omega. Because your T function has only exponential J omega T. So you can directly change this term to this term for your time harmonic case. Okay. So, okay, see the big red star here. We obtain 4 most important equations for this class. These four Maxwell equations, they are a differential form, time harmonic form. We will use these 4 equations again and again to apply to many places in our class. Okay? So every time, if you have a question in maybe midterm or final, you are looking for Maxwell equations, come to these 4. Okay? See? Okay, those are the common. Curl E equals to minus J omega B minus M. And curl H equals to J omega D plus J. And divergence D equals to low, divergence B equals to 0. Those are the most important 4 equations in this book. Okay? It's a beginning for many chapters. The beginning. Okay, we start from here. Alright? Are we okay? Okay. If you still have a question about the notation, you don't know who they are, try to check this. Okay, I have a list of what they are. But they are the time varying case. So you change them to time harmonic case. Okay? E is this one and this one. And the unit is very important. Unit can help you to understand who they are. Okay? I always read the unit, and I will always ask you about what is the unit for that. Okay? Right. And they are the phaser form. Okay? And so far we finished our first part. I already introduced Maxwell equations, and we will apply this one to many of them. So, after, let's go to next part. So, first part, remember what is Maxwell equations. You understand who they are, what they are for all the notations, what will you see in your midterm. Well, you should maybe guess what they are. If I give you some notation, then you can use this one to obtain other sign. Okay, this is the first thing you need to understand. The second one is, now we can apply our Maxwell's equations to boundary conditions. Boundary condition. Okay. What kind of question we are trying to deal with? The boundary condition means. Okay. Let's look at the Maxwell equations. All of them, you are looking at the electric field and the magnetic field in one single material, right? Like for the case we call that, this is air, free space for the question, because your D equals to epsilon multiply E, because this is air, so epsilon 0, right? And if you use epsilon 0 and mu 0, this is air, right? Okay. And if you have your field inside, maybe think about FR4. Okay, inside your board, FR4 board. Your epsilon equals to 4.2 multiply epsilon 0. And then your mu is also mu 0. Okay, different material, you use different parameters. But what happened for a case? If I have a printed circuit board, the experience, the project you are doing, you have PCB. You have this is FR4. Right? You have metal on it. You have metal down here. Okay. This is air, right? Air, you use epsilon equals to epsilon 0, and mu equals to mu 0. Can you see that? This is air. And then this is FR4. Inside the FR4, epsilon equals to 4.2 multiply epsilon 0. And the mu equals to still mu 0, okay? Let's make it easier, right? Okay, so Maxwell equations can apply to this part, also this inside, right? But what happened on the boundary? Who is right? On the boundary between two materials, which equation you should use? Okay. This is boundary conditions. Both of them should be right. But the choice is, you have only one choice, right? But at the boundary, you must be okay for epsilon equals to epsilon 0. But you need to also apply epsilon equals to 4.2 multiply epsilon 0. how can that happen? How can that happen? I cannot have two epsilon, right? For one boundary. So this is what happened. So we try to understand the boundary condition. This is something next we are discussing for a field on the boundary between two different materials. Okay? Okay, now you understand what we are dealing with, right? Okay. For only one material, it's just apply the Maxwell equation. But what happened on the boundary? So first of all, we changed a little bit from your time harmonic Maxwell equation. We changed B to mu H and epsilon E. Is that okay? And the mu and the H, it depends on the material. If air or free space, use mu is equals to mu 0. Epsilon equals to epsilon 0. So now you have this four new equations, Maxwell equation. This is the first step. We change according to this relationship. We change that to the yellow part. This is the first step. Okay. Now we try to write it down. Write down the notations. Okay. You have the E field. You have an electric flux density D, and the H and the B on both sides. Material 1 and the material 2, we can call that this is material. So this is material 1, and then this is material 2. It's not necessarily air, maybe another material. Okay. So we call this material 1 and material 2. Every field here we call it field number 1. Okay. Electric field number 1, electric field number 2, magnetic field number 1, magnetic field number 2. Okay, we make a name for all of them. So you got inside the material number 1, you have a material E for number 1, and the electric field E and electric flux density D, okay, and also B and H for that one. Okay. Of course, your E is supposed to have all the directions. For E and the D, they have all the directions. This is the result. Finally, this result will be used at the end. I post the result. This is the result. Okay. You should have all the E, all the D, all the B and H for the material number 1, and also enter the same thing similarly for the material number 2. Okay. So you have these 4 vectors. And first of all, we need to see. Maybe we can continue. Okay. And we have the source S here, rho as the surface rho here, and the MS here. 1, 2, 3. There are 3 sources. We need to find out a relationship between those notations according to our Maxwell equations. You must be valid here, and okay, still okay on the boundary. Okay. Okay. They are actually two different electric field, 2 different H field. But you need to know what happened on the boundary. Which field you should use on this boundary, right? Can anyone understand what I'm talking about? Okay? So, to apply Gauss's law, okay, I try to explain. This is, you need to use your imagination. Okay? If here is this is a boundary here. This is a boundary here. Maybe we can use something to help us. We have a boundary here, okay? Upon the boundary, it is material number 2. Down this boundary is above this below this boundary is medial number 1. Okay, this is a boundary. Okay, there's a boundary. You can think like we can use the Gauss's law. We use the Gauss's law to do the surface integral to a area, 3D area, okay, to something up and down the boundary, okay? Looks like this one. You can see that there's a cylindrical, okay? Just a cylindrical? Don't understand? Don't understand? Maybe I need to explain in Chinese. Okay? Do you understand what is the before we understand this one, we should know Gauss's law. Okay, let's a little bit review about Gauss's law. Let's see the equation of Gauss's law. This is Gauss's law. Okay, you have an area, spherical area. You take integration of the E field, or you can multiply upside. It's a D. You integrate the D will equals to how many charges inside this box. Okay? This is Gauss's law. You understand? Let me write that. To help you to understand. If you take the surface integral to the D, we can use a time harmonic, okay? Time harmonic D it's fine. And we use dot ds. This is a closed surface like this picture. It will become how many charges inside this area. Okay? Now, because I didn't tell you, it should be a spherical. It can be any shape for this area. It can be any shape. So we try to integrate a shape with, it looks like this is a cylindrical, right? Cylindrical. You have something, you have the height, and there are two areas in the top side and the bottom side. Okay, this is a closed surface, right? If the height of this one is going to 0, we can still call this a closed surface. But because of the height is 0, you can only deal with, you can make it easier. You deal with only the top area and the bottom area. There are only two areas you need to deal with. Just only the top and the bottom area. Okay. And you want to come back to this?
那其实记忆体流量只够刚好分解个。
Okay. For the next part, after boundary condition. Boundary condition is the first theory we applied Maxwell equations, okay? I hope you can remember what you learned for today. Maybe I will ask you next week. Okay. So the first thing, okay, you know the phasor form, differential, time harmonic Maxwell equations. That's the beginning. Then you apply this equation to obtain boundary conditions. Boundary condition means you have the electric field and the magnetic field in two different boundaries. What happened on the boundary? Okay, we obtain the relationship. And the second one, we need to know the wave equations. Let me write down the Maxwell equation. As I said, we will repeat to remember this one again and again. We use the curl E and the curl H. Try to remember divergence D and the divergence D. For the first equation, it is minus J omega, and then you use B minus M, right? And for this one, if you can remember, this is very professional and very cool, okay? So try to do that. Try to do that. Curl H equals to, you can J omega, something similar, right? D plus J. Okay. And for this one, it is a Gauss's law. Use the law, and it is 0. It's not very hard, not very difficult. You do that every week in my class. You can remember. Okay. Here comes the question. So, what is E? What is H? Well, let me ask you the first question. What is E? I told you at in last class, I asked maybe you, right? You give me an answer. What is E? For a general E, maybe E is you have the component of X and the component of Y and the component of Z. Remember that, right? There are 3 vectors for 3 different directions, X, Y, Z. You can also write down for a more general form. Maybe this is a vector, right? I define another scalar function. And it is a function of X, Y, Z dot the direction of X for this part plus E, Y, S, Y, Z plus E, Z, X, Y, Z. Okay? Can you read that? I write it very roughly. So this term is this one. You have the X direction, and this term is Y, and this term is Z. This is for just only X, Y, Z. We're talking about time harmonic. So the final E will multiply this term to the exponential J omega t, right? Remember, we take the J omega t outside. And this is the general form of vector direction X, the E field for direction X, E field for direction Y, and E field for direction Z. More. We need to understand about more. Can we simplify this one? Or maybe this one and this one. We can we take only this part, okay? When you see this is a function of x, and it is a function respect to x, y, z, and the direction is x, and actually you know nothing. Because this is any unknown, right? Can we try to understand, can we simplify this E to make it more general? What do we have to solve this E? This is what we do here, the wave equation. What is this? We try to solve this for more. We want to understand more about the E field. Okay? What will you see in your test when in your midterm? Can I give you another way to say this is? Can I give you any function and I told you that is E? Can I do that? Is there any rule? Is there any rule, anyone? What kind of rule we should follow? What? Which rule we need to follow? We cannot apply all the E, the function, for the E. No. We need to apply Maxwell equations. Okay? Every time we come back to Maxwell equations. Let's do that. So, try to solve E, just only E from the Maxwell equations. This is the wave equation. We try to solve Maxwell equation to obtain what is E looks like. What is the form of the function? Start from here. Enough space. Okay. So first, we copy the first Maxwell equation. Okay. Number 1 equals to minus j omega if this E field and the H field, they are in the air, which means it is sourceless. Okay? How can we change this equation? If this is sourceless, which one is 0?
N.
N. This is source, right? So, okay, we simplify. If I don't want to deal with B, I want to deal with only H and E. What can we change? B equals to
mu H.
Mu H. Mu is the mu for material, okay? So it's okay. Let's do the curl again. Can we do that for the left part and the right part simultaneously? 同时, okay? Take a curl to this term, and I take a curl to this term. Minus j omega mu, they are not a vector, cannot take a curl, right? So for H, I can take a curl. Okay? Can you follow? So I change the first equation to this one. Okay? Okay. Good question. What is the curl H? What is curl H?
J omega E.
What is curl H? here. J omega d plus J, right? But I say it is in the air, so there's no source. So it is J omega d. I take a J omega outside, okay? J omega d is epsilon E, right? Epsilon. Sorry. D is yeah. Okay? Because curl H equals to J omega D, and J omega D equals to J omega epsilon E, right? Okay. So for this part, it's very beautiful. Minus JJ equals to 1. JJ is minus 1. And the minus 1 times minus 1 is 1. Okay. Omega square mu epsilon E. Okay? This is ugly, right? I already write down the answer for that. This is a vector identity you can use. This one equals to this part. You can see from your appendix, you need to apply this one because you don't know the meaning of it. If you take the curl twice, it is a divergence, and you take a gradient, and minus, this is Laplace, remember Laplace, right? Laplace and the A. And the Laplace, I told you in the first week, yeah, the second week. So, for the left part, you append minus, this is not A, this is E. This is E. Okay, can I make it easier? As I say, it is a lossless. So there is no source, no source, no source. Right? I like zero. Zero make them easy, right? Zero. D is epsilon E, right? Which means divergence E is also 0. 0. Divergence E. Okay. Laplace E plus omega square mu epsilon E equals to 0. Okay. Remember this one, right? Right. Let me make the question much more easier. If I consider only direction of x, we consider only this part. Okay. can write down only this part. This is the wave equation. One equation, you have only the vector of E. Your vector E, your electric field, this vector function must obey this law. Not all the equation. This must be true. You have the Laplace operator. You have omega square multiply mu epsilon and multiply your electric field again. Your E field must obey this form. Then solve Ex for this partial differential equations. Solve this equation. Then the answer for this partial differential equation is the structure. How it looks like must obey your partial differential equation. This is the second order PDE. Did you learn this before? In your calculus class? They are doing this thing from Maxwell equations. Okay, let me show you the answer, okay? And you will know what will you see in your test for your electric field. They must obey this rule. I didn't use others. I try to simplify. I make it this 0, 0, 0, right? I only use this equation. I use only actually this 3. I don't use this one, right? I only use this 3. I take a curl to the first one. And I put the curl h. I put this for the curl h. And I also make the divergence E equals to 0. I apply these two, the result of these two into the first equation. Then I can obtain this is a wave equation. We make a big circle. Actually, you don't need this one, but you put an X, it's okay. Right? Because I use the total H, total E. But finally, you can make it separately. All the E field must obey. The X direction, Y direction, Z direction of the E field must obey this rule. Any question?
那个是不是算错了？应该是减吧，因为之前在推的时候都是
哪一个是减？
就是那个欧米伽平方前面那个应该是减号。
这里有个减号。
不是那个下面那个公式推出来，应该是那个
有吗？
可能是
这条有错吗？
一项那边有。
第二条有错吗？
第二条没错。
第二条没错，我这个有减啊。
这个有减。
按减提到这个可以。
因为我是直接用那个最下面那个公式直接推的，就是我是直接先。
没有减啊，这样对，你看一下。
就我以前推是有符号的。
你是哪里有？
就是
看一下比例好，
好，
我们 check 一下，会不会我推错？
好，
好不好？来算，我记得没有啊。我们看看，有错吗？我们是一起推的吗？我跟你们一起推的吧？答案有没有？ 有符号吗？
课本是这样没错。
所以是不同课本的关系啊。
我是照着我刚刚讲的所有事情。看一下哪边跟我的符号是不一样。Yeah, I do. Yeah, if you want to see more beautifully, you can see.
我知道，因为真的是用飞手计算，我用的是time value 计算，所以会查一个符号。
time domain.
对对对。
This is all time harmonic. We only take care of the space. And finally, if you have a question about for the final equation, you need to multiply exponential j omega t for the e. Because if you want to see the final total electric field. Okay? I think you can read. I use the green one means 0, 0, 0, right? You take a curl again for the left side and the right side, you get omega squared, and then you use the vector identity. This is the vector identity you apply. And you change that to this one, and for this part is 0. So you obtain these two equations. Okay. Wave equation. Solve your wave in only one equation to understand what does it look like for the sourceless electric field and magnetic field. This is a sourceless, only in the air or in the material. Do you have a question?
Low 为什么
Huh?
？Low
Sourceless, no charge, no
NJ
magnetic, no current density, no, there's no charge. I have only the E field and H field in the material, in the air, there's no charge. Okay, so 0, 0, 0, then it's easy to calculate. Everything is easy. Then you can do the same thing for H field. You take another curve for this term, then you will have similar thing. Okay? So those are the wave equations, two equations, wave equations. Very important. You will see this in many domains, maybe physics. They show PDE, partial differential equation for that. Okay, and the wave equation. Okay. Let's make it more simpler. We define k squared equals to this part. Okay? We define another notation k. We call k squared. We define that equals to omega squared multiply mu epsilon. Okay? Make it easier. We try to make the question easier and easier. The k, we call k propagation constant. When you propagate, you have some constant. We call that the phase constant. We also call it wave number. The k has three names. If we call that the propagation constant, means how it propagates. It is a constant for propagating. Okay? We call that phase constant. It is because K is related to phase. We call that wave number because K is related to how many waves in one something. How many numbers of waves we call K. Okay? So 3 names for K squared. If this is the material, it is lossless. Mu and epsilon, they are just, it is a lossless material, it is real numbers. Okay. Make it more simplified, or it is a very low loss material. If the loss is, okay, try to, you don't see the loss. Mu and epsilon, they are real number. Do you guys know real number? No? 你们知道什么是 real number 啊？就是实数的 number。Real number means 它就是一个数字，这就是一个实数，你知道吗？
实数啊，
相对的是虚数。If this is a lossy medium, K is not a real number. It is a complex number. You have a real part and an imaginary part. Okay? Okay. So after K, okay. So we make it easier and easier, right? Did you see that? It looks very easy to understand now. For E field, you need to apply this form, your wave equation. For H field, you need to apply this equation. Then we try to solve equation. For this one, this is a review for Laplacian equation, Laplacian operator, right? Remember this one? I told you in the second week. Laplacian. So this is to understand what is this for, and what is for this vector. You need to write down like. If you have a direction of x, y, z, you need to take the Laplacian of x, y, z. Then you need the component, take the second order partial differential to x multiply y, plus y plus z. You need to use these 3 parts for just only one direction. 中文就是你不只要对 x 做2次偏微分，你要对 y 做2次偏微分，也要对 z 做2次偏微分。你不能因为它是 x， 你就管 x 而已。这个 ax 它是 function of x, y, z。OK， 你们现在有办法搞得懂位置跟 vector 的关系吗？它第一堂课花很多力气在跟你们解释说，我不同的地方，它的 x、y、z 都会有影响。它虽然最后的结果是对 x， 但是你只是解决了，你不能只解决它的，它 y 跟 z 也会影响它。OK。Let me just a little bit introduce. I try to quickly explain this one, and I will repeat this again next week because this is very difficult but very, very important. Okay. So finally, we try to solve E. We try to solve what is the exact E. First of all, we need to know about. We try to simplify your general E field. We have the x direction, y direction, and the z direction. if I want to ask you question, I will rather you ask you only this part。这个刚才有讲过，对不对？我把我的题目减少到只有 x 方向就好。Okay. So for this part, you have the unknown. You have a variables x, y, z. Furthermore, I try to simplify this question more. If this ex is a function of only z, or maybe we can think about only t. We put the time harmonic back to the time varying. Okay? If this is a function for only z, 我们不要 x, y, z 当未知数，我们现在就只有 z 就好。但是它最后结果只有 x， 这是你搞得懂的事情吗？我的变数只要有 z。我现在已经用中文讲，你们是不是还是听不懂？已经只能用台语了。你们台语有比较溜吗？也还好。
变数 z 方向 x。
对，这样听得懂吗？我把题目更简单。我刚才一直跟你讲说，它可能有 x, y, z 的变数嘛，对不对？我现在就是不要，我现在有 z 当做它变数就好，但是它的方向是 x， 这样听得懂吗？就是更简单。我实际上是有9种可能的嘛，我剩1种就好。我只剩1种，因为我要解释这个最简单的题目给你们听。OK， if you agree with my assumption, which means your function of e, you take a partial differential to x and y will equal to 0, because you don't have the variable of x and y. 我们可以再做这个简化，你们是不是听不懂？因为你们听得懂跟听不懂表情差很多，但是听不懂就OK， 这个跟这个都是。So our equations, your wave equation down there can simplify to this. If this is a function of z and the direction of x, you only deal with the scalar part. 你不管向量，你只看它的存量的公式的话 ，you take the Laplace. You have only this part because x and y equals to 0, right? You don't have x and y. And these this term will left. This e function, this unknown function, take a second order of z plus k squared multiply your unknown function equals to 0. This is scalar equation now, and it's much easier. We change these two complex equation, general equation, wave equations, to only scalar equations with only unknown z, or maybe more t. Okay, z and t. I change this one to only z. I don't care about x and y because I want the question. I'm making the question easier. My wave can only change according to z direction, but my wave, the vector of E field is going to x direction. There are different things. Okay. Then I got my scalar equation. I obtained a scalar equation on this one. And this is easy to solve from your calculus class. You have something, take it twice, partial differential, plus some k squared. Okay. the answer, the solution of this equation is this. Yeah, you need to ask your calculus class, maybe 浩辉主任 for the answer of the second order PDE is this one. Okay. So maybe we should review this next week, but I want to finish that to something. Okay. So your electric field E looks like, I make a conclusion, okay? Your total electrical field E, if you want to simplify your total electrical field to, if you have only E direction, the X direction, if your E field has only X direction, equals to, this is a simplification, okay? I have X direction， 就是我假设它只有 X 方向，哦 ，OK， 那 equals to E X, and it is a function of only Z, okay? You can make it for the time, if you want to see the time harmonic case, you can multiply exponential j omega t. It's okay. But you don't want to see t. You just read at the black part. You can see that separated. 你可以把时间跟空间可以在这里可以分开看。你要看有时间就把它乘回去啊。你要看时间就是这样。你要看哪？你看有没有时间暂停？简单来讲就是这样。那我们现在在看的是空间上它会怎么改变？它是静止不动的哦。时间是 pause 的，时间是不动。那你要时间动，你就把它沉下去，它就会开始动，你知道吗？这个沉下去 cosine 就随着时间就会动，它这个是随着位置动，就这样子。那 your EX is can write down like the is a function of z equals to something. This is a number. This is an amplitude. 它是一个大小而已，就是一个数字而已。E plus 就是一个数字，就跟之前讲 V0 正 V0 负一样。Remember 上个学期我们在讲 V0 正面，它就是一个可能就0点几，就是一个数字，这就是一个代号而已。OK， 就是我刚开始学，你可能会很害怕，就是什么，我们就是一个就是可能一正它可能就是0.2，就这样一个数字，一个位就是一个代号。Multiply, so you got a exponential minus j k z plus another number multiply jk plus jkz. If you take my next semester's class, 那个射频无线通讯系统 ，you will see your voltage looks like that, right？ 我记得你们的那个电压是不是也是长得这样子？那时候我没有跟你讲原因嘛。我们现在是用 Maxwell equation 导到的。那这个是电场跟磁场 ，E field 跟 H field。Okay. Why you got this term? This is because it is the solution of this equation. And this equation, you have K here, okay? And then this is the equation of Z. When you solve this one, you got this one from the calculus class. 这个就是微积分的解，要去找这样。So every time you see the question of the electric field will looks like this form. Okay? Question? Okay. E field will looks like this form. And furthermore, if you want to deal with this, you want to see the time domain, you just multiply exponential j omega t, and this is j omega t and j omega t. You can write down this one like j omega t minus kz plus e minus exponential j omega t plus kz. Okay. Okay. Back to the definition of phasor form. Back to the definition of phasor form. You see, for this part, this is if you have some idea about what is that look like for the voltage, this is a positive wave to the positive z direction, and this is a negative wave to the negative z direction. For this term, you have two terms. This is positive E field and negative E field. 我们中文讲一次好不好？你算出来会有这两个，是因为你在上那个射频无线通讯系统的时候，你的电压不是也会分成 V0 正跟 V0 负吗？那也是前面乘一个这个跟这个嘛，对不对？那表示它的差别在哪里 ？Difference 在这里，它一个是减 kz， 一个是加 kz 嘛，其他是不是都一样？对不对？那这个东西 exponential， 你之前刚刚不是有说这个东西是不是等于 cosine omega t 减 kz 加上 j sin omega t 减 kz？ 那我只要看这一项，就是这一项就是一个 cosine 嘛。那 cosine omega t 减 kz 这个 cosine 波，它会朝着 z 方向前进。这个可能要把它输入进去，把这个 t 改变，它会朝着 z 方向会动。这样，一个是 t 改变，导致 z 改变。OK， 这边就是一个 cosine。那 one more thing I need to tell you before we finish this class。这个东西就是 theta， 就是 phase。我们在算很多电路，在用到 theta 或什么的，就是跟这个有关。我没有说都一样。你们在看的是 S11 的 theta， 它是去又回来的这一项。这个 phase 它是怎么造成的？是 omega t 减 kz。
时间跟位置。
好，这个下个礼拜会跟你讲很多故事哈。这个时间、空间、频率跟时间是有关，因为频率是一秒几次嘛，所以你频率、时间跟频率是在一起的。K 这个东西跟谁有关 ？K 这个东西刚刚有说它的定义是 omega 平方乘上 mu epsilon 开根号嘛，对不对？那这个东西它从这边的话 ，K 的话我要讲是它跟这个 z 是绑在一起的，它跟位置是有关的。这个 K 在射频里面，它会有时候是用贝塔来看，贝塔应该看过了吧？贝塔有印象吗？贝塔的定义是2派兰达，这个都是下礼拜要讲的东西。整个一个 phase 的周期是2派，长度的一个周期是兰达。2派里面它的长度就是 k， 就是贝塔，在这边是 k。那贝塔跟 k 在不同的传输线里面会有更复杂的定义，你要看你是什么传输线。我们现在讲是电磁波，跟那个都还没关系，但是你要从这边先了解。我们
你才有办法把它变成微带线，把它变成 waveguide， 把它变成 coaxial cable， 跟 ideal 的线，这些东西它都是同一套理论。OK，Thank you，赶快去买便当。